our last few lectures, we have introduced the philosophy behind regression, the utility of using regression technique in experimental dataset, and then we have discussed the theory of simple linear regression, the technique of doing simple linear regression, as well as how to test the quality of such regression. Now, in this lecture, we'll take up a small example of a practical dataset of engineering importance, and we will actually perform a simple linear regression over this dataset. Let us recall the rocket propellant problem that we have discussed briefly before. Here we are using a particular rocket propellant which is losing its shear strength with time, that is propellant age. In this table, we tabulate the experimental result. We have 10 experiments here, starting from this 1 to 10. And this column, X column, is the propellant age. That is 15.5, 23.75, etc., etc. Their age in weeks. In third column, we measure the shear strength in megapascal, and it's again 14.88, 11.57, etc. If I plot this as a scatter plot here, means I don't connect them with anything, just I plot the particular points, then you can see these blue dots are showing the scatter plot. In y-axis I have the shear strength in MPa, and x-axis I have age in weeks. Now looking at this plot, it looks like that it could be a linear type relation. It looks like that as the age goes up, the shear strength comes down, and they may be linear. With this assumption and without knowing much of the theory, we assume that there will be a linear model. Between this one input x, that is age, and one output y, we have this linear model w0 plus w1x. I am writing here y hat because this will be a least square estimate, as we know. We also know that this w0 and w1 will be given by the value of w0 and w1, which will minimize this function yi minus w0 minus w1 xi whole square, summation of that divided by n. Whatever there within this summation sign, that is something we call loss function. Every dataset has its own loss function, and the average of this loss function is something that we call cost function. The value w0 and w1 which will minimize the cost function, we are only interested in that kind of values here. Now in previous lecture we have discussed how to find these values by minimizing this cost function. We will not discuss that once again. We will simply use the mathematical expression that we have derived in previous lectures. We know that this w1 will be given by sxy divided by sxx, and once we get the w1, the w0 we can get from y bar minus x bar w1. The expression of sxx and sxy are as follows. Sxx is xi minus x bar whole square, summation of that, and sxy is xi minus x bar multiplied by yi, summation of that. You can write here yi minus y bar, that doesn't make any difference, but that is also a right expression. For this study, writing only yi is perfectly all right. Now we need to know the x bar. X bar will be summation of xi divided by n. So summation of this entire column 2 divided by number of data points, that is 10. That will give us the average value of x which is x bar, and if we do that calculation, it turns out to be 13.375. This is a very simple calculation. You can use a calculator and perform the calculation. So this is 13.375. And then once I get this 13.375, I can find out this SXX and SXY. This XI, individual XI minus this X bar, I calculate, multiply with corresponding YI, and then I sum it up. That gives me negative 131.31. Similarly, SXX gives me 519.15625. This is SI minus X bar whole square summed over. Therefore, I am ready to have this W1, which is SXY by SXX, and this as SXY is negative. This is negative. Now we can calculate W0. It requires Y bar. So Y bar is here 1 upon n summation of Yi, means this third column I'll sum it up and then I'll divide by 10. That will give me Y bar, and it turns out to be 14.554. So this W0 now I can calculate, and it is coming 17.937. So I have my results W0 and W1. I can plot this result, but before that, let us see that how we can perform this calculation in a computer program. There is no actual advantage of doing this in computer program instead of doing this in hand, except the fact that in manual calculation you may do some mistake, but computer will not do it as long as you have given the correct data input. So here we are using a Python program for calculating W0 and W1. The actual program will be much longer because we have to plot the results, etc. But I have removed that part. Here we can make use of this NumPy package of Python, and my array calculations will be much easier. Only that I want to show here. And I am using here the primitive formula that we have deduced first, and then we have changed this so that it looks better. But for the calculation is in computer, you can use any of them, it doesn't matter. So I have to calculate X bar, Y bar. Here X is the input array in NumPy and Y is the output array, that is the propellant shear strength in NumPy. And N is the size of this array. You can take any one of them. Now X bar will be NP sum X, and this NP sum will actually sum of all the members in X, and then you divide by N, which is the size of X. That gives us average X. Similarly, average Y is NP sum of Y divided by N. Then I need XY bar. To get this XY bar, first I carry out a dot product of XY. So XI, YI summation will be the dot product of XY. X and Y are two vectors. Their dot product will be X1, Y1 plus X2, Y2 plus X3, Y3, etc. I take that scalar product, divide by N, I get average value of XY, and X2 bar, that is once again NP sum of another vector, which is this NP square X. This NP square X will square each element of X individually, and it will give us back a same size array. So this NP square X, then I make a sum of all these individual elements which are already squared up, divide by N. Now I can use this formula W1, W0, and W1 is XY bar minus X bar multiplied by Y bar, etc., etc. W0 is Y bar minus X bar multiplied by W1. I can calculate y hat, and after I do this calculation of y hat, I can plot the results and check for r and r square, etc., which I am not showing here. You can do those calculation very easily. So this results, you can analyze it further, of course. This calculation you can perform simply manually, or you can use a spreadsheet. Of course, in computer program here, you will have more accurate results, since you can consider more digits after the decimal point. In actual manual calculation, you will have to truncate after 1 or 2 numbers after the decimal. Python also has its own inbuilt routine. In Python scikit-learn as well as in Python SciPy, you will have the inbuilt routine of regression, not only for linear regression, also for other type of regressions, and you can use that as well. Now at the end, if we plot the result, these blue dots are the scatter plots, so they are showing individual data, and this green line is our regression line. The difference at each point from this blue dot to green line, this is showing our EI or residual at each point. The least square algorithm, what it does is that at each point it builds a square, and then it attempts to minimize the area of all such squares, the summation of that. In minimizing the summation of that, you can see that the line is not passing through any of them. Probably it is passing through this, just touching this point. But other than that, it is not passing through any of them. But overall, it has minimized the total area of all such squares. Now, how good is this area minimization, or how good is our algorithm? You know that we can evaluate that from r and r square. So you remember that we have this correlation coefficient r, which is sxy divided by root over sxx syy, and this you can calculate. Sxy, we have already seen that this is negative, therefore r is going to be negative, which is minus 0.927, and r square is simply square of this minus 0.927, so it will give us 0.86. Is it good or is it bad? That is for you to decide, or for the user to decide. The calculation will not tell us anything. What we can say that r is negative, it is telling us that as x increases, y is decreasing, and that trend is captured very well in our regression line. R square is 0.86. That tells us that it captures reasonably the variation in the data. That regression line captures, it's more or less okay. That is why we are using this word, it is close enough. Is it enough or not enough? That is for you to decide, but 0.86 is usually a good number. Anything close to 0.9 is usually a good number. Going to too close to 1 is not necessarily good all the time. So now we have some idea about the regression of this particular data set. If we want to know what will happen to a propellant shear strength at 10 weeks of age, then we can simply come to 10 and check the corresponding data point here from this line, and that will give us the least square estimation of propellant shear strength at the age of 10 weeks. Then another point I want to mention is that you will see that this average here about 13 and 14, the x bar and y bar, that will fall exactly at this line. You can check it out that for yourself, but the regression line always will pass through the x bar, y bar exactly. That is a mathematical truth. So now to summarize, we have now seen an example of a simple linear regression. For your exercise, you can take this function y equals root x, generate 5 equidistance data point on it in the interval of 0 to 2, and then using the method we have discussed, you fit a straight line through this point, calculate the value of r square and discuss its significance. Here, my suggestion is that you don't have to use a computer program, right? Do your calculations manually. That will be sufficient, and I think that will give us more of a feel about the problem now. Thank you. That's all for this lecture, and I'll see you in next class.